Uh, uh,
Okay, so yeah, Yanan, please, whenever you're ready.
okay. Uh, Thanks for Professor Smith's invitation. Today I'd like to talk about the derivative estimates of Floricos. And firstly, let's review some basic notions of the Floricos. It is a parabolic flow of Hermitian matrix introduced by Streets and Tien. You can write it as like this. Use the decimal Ricci form. Here, the row 11 is a 11 part of decimal Ricci. Equivalently, uh, we can formulate it as with using the Chen scale construct. Here, S is the second Chen scale, not sorry, the second Chen Ricci function. And the Q is the quadratic term defined by the portion of chain connection. Here T is the portion. And this flow preserves the Flory-Close condition, which is θ equals 0. And under this condition, we have that the one part of the discrete form can be written by the second term ridge plus the Q. And the relationship between the Floricos flow and the generalized Ricci flow is actually they are they are the same up to a gauge. More precisely, if GT is a solution to the Floricos flow, then we have that. We can rewrite it using the bridge of Levi-Slater connection plus the decimal torsion form. Here the theta is waveform. Here the Beeson portion is defined by and the leaf form is a form defined by this. So it is just uh, it is just a generalized Ricci flow up to a gauge, which means they are the same up to a diffeomorphism generalized by the vector field theta. And notice here an interesting thing to notice is that the right hand part is just half of the generalized Ricci flow. In general, the generalized Ricci flow is we have two rich. So it is just a half, which means we need to make a rescale on the time. And from the theory of generalized Ricci flow, we know that we have a compact result like the Ricci flow, which means uh, if we giving or which means giving a family of for example use giving a family of generalized Ricci flow with bounded or with bounded remaining curvature. Then we can find a convergence subsequence. This is a classical result, uh, like the Ricci flow. Uh, uh, but for in complex geometry, the Chen convection is more natural. So we would like to ask, can we exchange the condition by Chen curvature? We use omega to denote the Chen curvature. If the Chen curvature is bounded, can we find a convergent subsequence? A theory given by Spitz and Tian tells us that maybe uh, in, and in 2010 or 9, sorry, I can't remember precisely. It tells us that if the Chen curvature and the contortion and the gradient of contortion is bounded. Then we give you a family of Florida's flow, such that those are bounded. Then we can find a subsequence, a convergence subsequence. And today I'd like to generalize their results. We prove that actually we only need the condition that the contractor is bounded. Then we can find we can give estimate of higher order derivatives, and we get a compact theory. And more precisely, we like to state this theory like if GT is a solution of Flory closed flow. On a complex manifold. And giving some positive number, then giving any integer, there exists constant depending only on the dimension of manifold and the given constant, such that if then Chen curvature is bounded for points in this interval. Then the derivative of the curvature here D is the Chen connection is also bounded. And the derivative of torsion is also bounded. For all points in the same interval. This theorem is similar to the classical theorem for Ricci. And here we have a little difference that that relationship between the time and the bonds is not linear, or t and 1 over t not linear here, since we need to deal with two equations, the equation of omega and the equation of t in the same time. So maybe we cannot acquire that we can get the same results as well as classical algebra. But this form is enough to give a compact result. So we can,
So,
if,
Jan, I mean, is
uh,
it not scale invariant, this estimate?
so sorry?
Is the estimate scale invariant?
Yeah, yeah.
Oh, okay. But then I mean, I don't think I understand what you mean. It's like not as good as like the classical Ricci flow case then. But what do you
Uh,
mean?
I mean that the the relationship between the bonds and time interval. In the classical results for rich flow, uh, if the bond is K, the rich, then we can obtain the estimates in the time interval, the relation may be K minus 1 for tau. The length of the estimates in the time interval. Here the relationship between T and the bounds of culture relationship is R is T and
Oh, okay.
K square. Although this is not very important for us
Oh, okay.
if we only need
Think I see.
convergence results, because we only need to have a little interval in the time. It is enough.
Right. Oh, okay.
So as a result, we can obtain a compact theorem that if we have a family of fluid flow with uniform bounded chain curvature, then we can obtain or we can find the convergence subsequence. Right. And like a rich flow, another basic question when we needed to when we deal with the finite time singularity is that the non-collapsing results along the flow. Uh, for rich flow, this is a pyramid work, and in the generalized rich flow, here actually in general we do not know. We are still the general case is still unclear. We do not know if it is not collapse. But in some special case, we know the flow is non-collapsing. For example, this is we can find this result in the book written by Garcia Fernandez and Spitz. See this book. Uh, for generalized rich flow, uh, one reason is that we do not know is it not collapsing, is that the double entropy or the inter entropy is not monotonic in general case. But they find conditions that if we have this condition, then we can modify the definition of a double function and then we can get the local collapsing result. This condition is that if we have a solution to generalize the rich flow with a function, for example, phi satisfied this is the convection defined by Levis Vita. This is the Laplacian defined by the Levis Vita convection, such that which means it compounds the evolution of the Bismuth portion. Maybe this condition seems a little strange in geometry setting, but it is natural from the analysis. And actually, if we recall the relationship between Coriolis flow and the generalized Ricci flow, we can find that in some special case, actually, this condition is very natural, and we can find many cases that satisfy it. We will call that the Coriolis flow just the generalized flow half of the generalized flow up to a gauge. This gauge is a special one because it is generated by the leaf form. So next, we'd like to give, for example, here we consider the heat equation and we will call it heat equation. We use this to denote the Laplacian defined by the Laplacian with respect to the Levi-Civita connection using the complex coordinates. It can be like and use this to denote the chain connection or the half chain connection. We just omit half. So If we assume U is a real function, then we have the relationship that half since is received on half the uh, classical Laplacian is the Laplacian plus their theta is a leaf form. We recall that it is defined by this. This is the inner product induced by the metric. The half is because we define the Chen Laplacian just take half in Chen. We have this relationship and assume that you satisfied this equation. F is another function, real function, and let yt denote the family of general generated by minus theta. And we set S in half time. Then we compute the involution equation of utility, which is defined by which is brought back by the morphism. Theta is U times since S is half T. By definition, it is just this. And gener generated by this vector field. Well, it's just and a computer computes the Laplacian induced by the metric, a pullback of the metric. Since all thing is pulled back by the morphism, so we can exchange them that we obtain. Then using this relationship, we obtain this is just 2 times. Sorry, let me see. Oh, sorry, here maybe we do not need this minus. Okay, just generate by Okay, sorry. So utility satisfies by assumption we have it's just and notice that this means that since the Floricos flow is just a half, because the right-hand side part of the equation is half the generalized flow. So which means that if this is Floricos flow and we have some function like this, and here is the corresponding generalized Ricci flow. They are equivalent because they are just generated by a diffeomorphism. So this condition, then the condition given by Spitz and Garcia Fernandez, this condition is just like we find a function that a real, oh, sorry, I forget that. Here we need phi is negative. Find a phi such that since the norm of the Bism portion is the same as the norm of Chen torsion, but this condition is very natural from the complex setting. If the initial date satisfies the class of the potential of all of the torsion is zero, we just need the class is zero. Then we can find a 2-0 form beta satisfies this equation, and we just involve the beta by the 2-0 part of the Bismuth form from the beginning initial data. Then we must have that the norm of the beta is just less than. The last term is defined by this, for example, if I the so and U S are you are x. Uh, or in normal coordinates is just trace the beta times beta bar by the metric and the q, since q is non-negative. So uh, this quantity is a non-negative number, and we have this. So this condition is very natural in the complex setting. And in this, under this assumption, we have that the flow, the particles flow is non-collapsing. So this uh, deal with times in P if for this flow and it is finite times linearity, then we can deal with scale and get the family of particles flow, and using a compact theory, we can scale it by the temperature. Uh, for example, we have X Ricci flow, the classical method. Okay. Uh, I forget it there. It's also let's let's begin with this part. This condition, if we have this condition, then the extra condition or the extra controlling equation given by Bessel and the secrets is satisfied, is automatically satisfied. Then in this case, then if the flow meets a finite singularity point, then we can scale like you know like the classical Ricci flow. Here lambda is the maximal of the curvature the of the norm of the chain curvature, and we obtain a family of vectors below. Then from the compact theorem, we obtain now, and since we also assume this condition, so we also have the non-collapsing results. Then we can obtain a singularity model. But in general, we do not know when the east flow is not collapse. And notice that this condition is actually is very maybe is easy to or there are many examples of this condition. For example, if the manifolds have Fediva lemma, Fediva lemma, then then For any pluriclose metric, since this is closed for any pluriclose metric, then using the DT lemma, we can find since this is since it is the bar exact, so in the bar exact, then we can find two zero part. So it's zero in the class, especially on Cantor manifolds. It is always true. And this is also true for the commission symplectic form. Since since one of the condition of one of the sorry in the definition one of the condition of the commission symplectic is that we need a trivial form satisfies this equation. So okay, this is what I'd like to talk about the non-collapsing results. And we go back to the derivative estimates in dimension 2 in the surface case. We give we give an estimate of the torsion using the not sorry, using the Ricci curvature of the concatenation. Formally, if this is a solution to the Floricos flow on compact surface, complex surface will assume this flow existing on some interval. It can be a global solution, and if the Chen reach is bounded. Here reach is a classical Chen reach and S is a second Chen reach. They are different in general. For non-Taylor metric, the sum of the two reach is bounded. The classical is increase in the last two subscripts, and the second is in the first two subscripts. And this operator, the S operator is always elliptic, but this is not always elliptic. And in Taylor case, they are same. Then we can find maybe want to say a universal constant, such that the portion, the norm of the portion is bounded by the ridge curvature or the initial data. Here, I'm not sure. Uh, can we get an estimate that independent with the initial data? Since maybe we can find a rich flat but non-Kähler metric, then then maybe we can do the scale. But I'm not clearly that if it is rich flat, then actually it is flat, or maybe it is unique in dimension two. And if we have this theorem, then we can give another proof of the uh, results of street and plane in dimension two. Uh, they show that in general, in every dimension, if the decimal range, the right-hand side part of the inversion equation, if it is bounded, then the solution is global, or the solution can exist for a long time. Uh, here in dimension two, or actually in general, we always have the relationship between the decimal range, the one part of decimal range. So the difference between the one part of a decimal range and the second range is just a q, which is it is its norm is Gaussian square. So in dimension two, if those two range is bounded, then from theorem B we know that this is also bounded, and we can obtain a one-one rebound. The then the solution is global. So we can also get the long-time existence from the boundedness of the Chen ridge. And I have a question about this. Here we know that uh, if the curvature, the Chen curvature is bounded, then the solution is global. This is results from theorem A. Theorem A, yes. And in dimension two, the most important case or the most interesting case we care about, uh, we find that if the reach is bound, then the solution is also global. So I'd like to ask a question that if the, or in dimension two, if the scalar curvature, the Chen scalar curvature is bounded, then the solution is global. Mm, it is global. Why I'd like to ask this question? This is because in the Keller case, at Ricci flow, this is the result of Hangzhou. It shows that for average flow, if the scalar curvature is bounded, then the solution is global. And in the rich flow case, this is Formler's work. They show here this is real scalar curvature or the Riemann scalar curvature. If this is bounded, then the singularity point C is, is dimension 4. Or singularity set is dimension 4. Or dimension 4, sorry. Yeah, this is generalized. Hamilton conjecture. So I hope that in dimension 2, since here this is a flow of complex geometry, so maybe we do not have any singularity. Because for rich flow, from the proof that the singularity equal dimension 4. Maybe this is also true for generalized rich flow, but I don't know. Maybe it is true. If it's true, then maybe it is equal dimension 4. So the singularity point is is has a lot. And for complex geometry, maybe we have. I hope there do not have singularity if the scalar curvature is bounded.
Yanon, maybe I just make a comment. I think using this, I guess here R, you maybe mean Chern scalar, is it right?
Yeah.
So I think if you use the basically this modified scalar curvature for which we found this monotonicity formula.
Oh yes, I know. The
Then
modified
I think you
scalar.
can probably prove that if the scalar curvature is bounded and you stay inside this like positive cone, this like positive Epley cone, I think you can probably prove.
You're using the modified scalar curvature.
Yes, exactly. Yeah, I'm pretty sure you can prove. Yeah, if that thing is bounded above um and you stay inside this positive cone, then the solution is smooth.
Oh, okay. Oh, sex.
Yeah.
I remember this because the modified scalar curvature is more natural for the generalized rich flow.
Yeah.
Uh, okay. Thanks very much. Uh, I will show why I'd like to ask this question because the in the proof of theorem B, the Chern-scale curvature looks like natural. So I ask this question. Maybe the maybe the weighted scalar curvature is more natural in this case. I will check it. Thanks for this space.
Sure.
And next, before we give some proof of this two theorem, I'd like to talk about more about the Hermitian selector case, or the special case that is non-collapsing, which means that we have the class is zero. Uh, Actually, this result is just a little adjustment of the proof of split to the steady soliton on Kähler manifolds. We have that if omega is a soliton of the flow, and if the class is zero, then we have that it is Kähler, which means actually this is real. Actually, this is a little adjustment of Professor Spitz's proof. The key observation is that the evolution equation of beta, the torsion potential, is invariant under under normalization. More precisely, this is the initial flow, and if we do some normalization like this, for the initial flow, we have the evaluation this, and if we denote the solution to the normalization flow by delta. Actually, this equation is invariant. So, up to a normalization, omega tilde is always the stated soliton. If omega is a soliton of vertex, so maybe it is expanding or shrinking or stated. Up to after normalization, omega tilde is also stated the soliton to the normalized flow. And in this case, since it is stated, this is just where x is independent of time. Oh, good. Since it is stated, so this equation becomes an elliptic equation. The strong maximum principle tells us beta must be a constant and t is zero. So actually it is Kähler. This is just a slight adjustment to the streets proof. Actually, this result uh, 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 we have known it, but we have known it in using different method. For example, in the expanding expanding case, since we have the expanding entropy defined by space and Tian for generalized Ricci flow. So all expanding soliton is trivial, which means H is zero or is scalar. And the steady case, from the definition, the theorem of a result of Professor Smith, we know that the steady soliton must satisfy this equation, where H is the Bismuth torsion. So if we add the assumption, then by direct computation, you know it must be canon. And the thinking case is more difficult, but from the book we mentioned above, we know in this case we can find the control function. So we have the shrinker entropy now. In this case, it is monotonic. So under this assumption, the shrinking solution is also Kähler. Here we just give uh, another proof of this. Uh, all I want to say about this is that maybe this condition is more this condition is more like the generalization of a Kähler case, because in other conditions, if the class is not zero, if the class is not zero, maybe in this case, if the class is not zero, the behavior of flow is more difficult, and we can find many really non-Kähler solitons. We still have many time, and I'd like to give the proof of the two instance. Just to give a speech of the proof. Uh, Firstly, we give the estimate of the torsion using the curvature. We have a lemma which reformulate the Florica's condition. It is said that if a metric is Florica, then we can rewrite it using the Chen curvature. It changes the subscripts. So actually we know that if the metric is scalar, then we can exchange the subscript. And so under the torsion is zero. So scalar is always very close from this equation. We can also find that. And we can prove it by direct computation. Notice that, let's notice that this is the crystal popular symbol of the Chen convection. And it is just the second order part is I, J, and the other first order part. And we sum those, we can have that the second order part is like this is the second part of the left hand side, and this is just the Floricos condition in local coordinates by direct computation. So from this lemma, we know that if we always assume the curvature is bounded in our theory. So from this, we know that if the curvature is bounded, then the torsion is way to increase. Actually, we know that it increase the torsion is just scalar curvature, some different scalar curvature. The torsion is also bounded for some universal constant C. Actually, for Floricos metric, the estimate of torsion by the curvature is pointwise and it is independent of the flow. So we can always assume the torsion is bounded if the curvature is bounded. Next, we give the, and from this equation, we can easily to see that if for Floricos metric is Chen flat, the Chen convection is flat, it's Chen flat, then it must be Kähler, and from the uniformization theory for Kähler manifolds, we know that its universal covering actually is Cn. So with a standard metric, Cn. So Chen flat is not a very good condition in our setting for Floricos metric. Pism convection, Pism flat is more natural. And we actually we have a non-Kähler Pism flat example. And also for the Kähler-like condition, it is same. If the Chen convection is Kähler-like, or we call it a Chen Kähler-like, then it is also Kähler. So very close. The Chen Kähler-like is also Keller. So maybe we'd like to consider Bism Keller-like for the flow. And next, we give the estimate of a gradient of T. Here we will give some notations. We use D to denote the Chen convection and split it to the 1 parts and 0 parts. And the Chen notation we need half for convenience. Another half we denote it, and the relationship between this and the whole Laplacian is just a rich term. And the entry identity, especially the first entry. Actually, from the first version, I think we can rewrite this. Actually, the left hand side part is just like this. So if a Florico's metric is whose torsion is parallel, so Chen parallel, so it is also parallel. So maybe for Florico's metric, all those conditions we add if we consider some very non-cater examples, all the conditions we add to maybe the Bismuth connection. The condition related to the Bismuth condition is more natural, although it is more difficult to compute. And the second branch identity. The branch identity for Chen connection is very simple, but it is very difficult, very complexity to the Bismuth connection. And maybe for convenience, we also write we maybe omit the metric. The taking principal metric, we use the same notation. If the subscript is the same, we omit the metric. We use the same subscript to denote the trace given by the metric. And I'd like to give the evaluation equation. Here the evaluation equation of the curvature is the gradient bar. So from this equation, we know that when we deal with the gradient of the curvature, we also need to deal with the gradient when we will use the term that the gradient of curvature and the gradient of t. So we need to deal with both gradients, and we have to modify the classical method for Ricci. And the evaluation equation portion is like this. Here we write more precisely that the T and T bar is different since we have the first definition. We have that T bar T is just the curvature. So d bar t, we do not estimate the d bar t because we needn't estimate the d bar t since we assume that omega is bounded. If we do not write more precisely, maybe the estimate of gradient t is more difficult. So actually, we just need to estimate the total and the partial derivative. We only need to estimate this term is all the total derivative. We have the lemma status. This is just a our proof is we will prove by induction. So actually we only need to estimate this one. This. If we estimate the gradient portion. And if A is a tensor, which is the evolution equation of its norm, it is just this. Under the assumption that curvature is bounded, from the lemma we know that the portion norm is also bounded. So these terms are good terms. They are just bounded by basically the good terms, and we use this term to bound some terms given by the evolution equation. Here, using this lemma, we know that if we estimate the gradient of t, the most important term is this term because we will appear under the gradient of t, the estimate of the bounds of gradient the bounds of gradient of t given by the evolution equation of t sphere. So formally, the first step we give the auxiliary function defined by uh, alpha is a constant determined later. And actually here we can choose basic difference. And by direct computation using that auxiliary corresponding evolution equation is that we can give the terms gradient of t and the country. Then we can estimate AT. Actually, we compute using this function. We define function theta is also constant later and in this function we know that the gradient of t is bounded and we can obtain more of given by the evolution equation of gradient of t. So by maximum principle, we obtain that and remember that this is just using the first differential. So we it's obtain the estimates of gradient t, and then we need to consider pair of the function. We need to estimate with two at the same time. Just consider this one. We can move on. So we can obtain the estimate from maximum principle and recall the relationship between the total gradient and the partial gradient. Then we can calculate our output by induction to estimate these two terms in the same time and define the function by induction. And the equation is similar. Then thus we complete the proof of theorem A. And theorem B, actually the method is very easy. We just need to compute the evolution equation of the ocean more precise. We have this if we really consider clearly that mm, there is the first order term on actually the fourth order of a norm is a minus, it is a good term. So if this term, the rich is bounded, then we can obtain the estimate from the maximum principle. And this one will, and we complete the proof of CMB. And I'd like to talk why we ask the question that if the scalar curvature is bounded, can we get the estimate of ocean? Uh, uh, because this term will experience in the evolution equation of scalar curvature. It will appear in the equation. Although there are many other uh, terms like this, but they have a different type of construction. So maybe actually I'm not complete the history, but I guess maybe we can get a better, a good estimate
Oh, sorry, Yanan.
from the
For
see
this one, the do you really mean nabla t to the fourth, or is it probably squared?
here. Oh, so this moment is here. That's
And the first term, is that it says like is it Ricci plus Q, or what is it?
uh, it not the Q, it maybe the Q3 in your definition because it contract by the first two terms. The Q is defined by contract the last two, the last two subscripts.
So
This is
that's what's
contract by
appearing
the
there. That term is Q3.
yeah, maybe it is Q3. This is just a Q3.
Oh no, it's
No, no,
oh,
no, no,
that's
no,
an
no, no, like
S.
this.
That says Ricci plus S. Is that what that says? That's what I was
Uh,
confused about.
this is like if we use the matrix notation, this is this of 2 times h plus s.
No, so my question, I think I understand that.
Uh,
I just want to know the quantity with indices A, B bar. That's Ricci plus S, right? Is that what that is?
yes,
And the
yes.
Ricci is just Riemannian Ricci, and oh, is that what it
Uh,
means?
this the rich and the S are all the rich of Chen connection. This is a classical rich of Chen connection, and this is a separate rich.
Okay. 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 Thank you.
And in a special case, if the ratio, the true ratio is also positive, actually, this is bounded by the scalar control and sphere we have two. If the all eigenvector is positive. or if the all eigenvector is negative, they have the same symbol, then this term can be estimated. The difficulty is that if the one eigenvalue is positive and another is negative, then this one cannot be bound by the skeleton tree. But we have another equation, this equation. Maybe we can we can show that if the skeleton tree is bounded, then the portion is also bounded. All right. Yes, that's all I want to talk to do. Thanks. Any questions?
Okay, yeah, thank you.
Thank you.
Um, well, yeah, I don't know, Bestie, do you have any questions? Okay, maybe I'll stop the recording.